Hey everyone, welcome back. This is the second video of the three-part video series where we are trying to learn how RAG works. In the first video, we understood how RAG works under the hood and we also looked at the architecture diagram. So if you haven't watched that video, I would highly suggest watching that video first and then come on to this video. But if you already know how RAG works, then it's all good. You can continue watching this video. So in this video, we will try to create a simple RAG application where we will try to load and split the PDF files, and then we will also use OpenAI's embedding model and then creating a vector store using FAISS, and we will try to retrieve the relevant document as per the asked question. So that's what we are going to do in this video, and then I will also give you a line by line walkthrough of the code. So before we get into those things, let me quickly show you what you will be building by the end of this video. And as you can see, it's a fairly small notebook, and with just few lines of code, you will be able to build a very powerful application where you can provide PDF documents to your large language model and you can ask questions related to that. There I'm asking this question: what are the key findings of Apple's paper, The Illusion of Thinking? If you haven't read this paper, it's a very interesting one. I highly recommend checking out this paper. Or if you need a detailed video on what all things are discussed in that paper, do let me know. We can do a video as well. So I asked this question and this is the response I got, and it's a fairly good reply. And I'm not going to read the whole thing, but yeah, the response was pretty good. But if I had asked this question without indexing the paper, then maybe the LLM wouldn't have known what I'm talking about. Now let's take a look at the code and understand each and every line of code. Before we start looking at the code, let's make sure we have everything set up. You will need to install Python if you don't have it already. And after that, you will need to install packages like LangChain, OpenAI, Facebook AI, Similarity Search. I have installed the CPU version. You can install GPU version if you want to do that. And then you need to install TickToken and then PyPDF. Make sure to have those installed in your virtual environment using pip. You will also need an OpenAI API key. You can get one by creating an account on OpenAI's platform. Finally, make sure you have a directory with PDF documents that you want to use for question answering. Let's start with our configuration file, config.json. This file helps us keep our API key and directory path organized and avoids hard coding them directly into the script. As you can see, it's a simple JSON file. OpenAI API key is where you will store or put your actual OpenAI API key. Make sure to replace your OpenAI API key with your key. Data dir specifies the relative path to the folder where our PDF documents are stored. Here it's set to data, and vector store dir tells us where you will save the vector database created by FAISS. Here it is going to be vector store. Using a config file is good practice because it makes your code more portable and easier to manage. You can change settings without modifying the core code. Now let's take a look at all the import statements. First, we import JSON for reading our config.json file and OS for interacting with the file system, like listing files in a directory. From langchain.chains, we import retrieval QA. This is the core class that orchestrates the entire RAG process. It takes a language model and a retriever and combines them to answer questions. From LangChain OpenAI, we import chat OpenAI. This is the class we use to instantiate the OpenAI's chat model that we will use to answer our questions. From LangChain community.document loaders, we import unstructured PDF loader. This class is responsible for loading the content of our PDF documents. It extracts the text from the PDF and parses it for further processing. From langchain.textSplitter, we import recursive character text splitter. This class is used to split the loaded text into smaller chunks. This is important because language models have a limited context window, so we need to break down the document into manageable pieces. From LangChain community.vectorstores, we import FAISS. It stands for Facebook AI Similarity Search. It's a library for efficient similarity search and clustering of dense vectors. We will use it to create a vector database of our document chunks. And the last one is OpenAI embeddings. This class is used to generate embeddings of our document chunks using OpenAI's embedding models. These embeddings capture the semantic meaning of the text and allows us to perform similarity search. Now let's load the configuration from our config.json file. Here we use the open function in a with statement to open the config.json file in read mode. The with statement ensures that the file is properly closed even if error occurs. JSON.load reads the JSON data from the file object f and parses it into a Python dictionary, which we store in the config variable. Then we extract the values for OpenAI API key, data dir, and vector store dir. This makes it easy to access these variables throughout the rest of our code. Next, we have the load and split PDFs function. This function is responsible for loading the PDF documents from the specified directory and splitting them into smaller chunks. The function takes data directory as input, which specifies the directory containing the PDF files. Inside the function, we initialize an empty list called alldocs to store the loaded documents. We then use os.list directory to get a list of all the files and directories in the specified directory. We iterate through the list of files and check if each file name ends with .pdf using filename.endswith. This ensures that we only process PDF files. If a file is a PDF, we create an instance of unstructured PDF loader with the full path of the PDF file constructed using os.path.join. We then call the load method of the unstructured PDF loader instance to load the content of the PDF file. The load method returns a list of document objects where each document object represents a page in the PDF. We extend the alldocs list with the list of document objects returned by loader.load. After processing all PDF files in the directory, we check if the alldoc list is empty. If it is, we raise a value error with the message no PDF found in the data folder. Next, we create an instance of recursive character text splitter. This class is responsible for splitting the loaded documents into smaller chunks. Chunk size equal to 1000 means that we want each chunk to have approximately 1000 characters long. This value is a trade-off. Smaller chunks might be more focused, but larger chunks retain more context. So you need to decide on a value that works best for you. Make sure the value is not too small or too large. Chunk overlap is equal to 200 means that we want each chunk to overlap with the previous chunk by 200 characters. This helps to maintain continuity between chunks and prevent information from being lost at the boundaries. We call the split document method of a recursive character text splitter instance, passing in alldocs list. This splits the documents into smaller chunks based on the specified chunk size and chunk overlap. The split document method returns a list of document objects where each document object represents a chunk of text from the original documents. We store this list in the chunks variable. Finally, we return the chunks list. This chunking strategy using recursive character text splitter is smart. It tries to split on sentence boundaries, then paragraphs, and so on to avoid cutting off mid-sentences. And here I'm just calling the load and split PDF function and passing in the data directory. And in this line, I'm just printing the number of chunks that have been created just to verify whether everything is good or not. Next, we have the create and save vector store function. This function is responsible for creating a FAISS vector store from the document chunks and saving it to the disk. This function takes the list of document chunks stored in chunks variable and the directory where the vector store will be saved as input. Inside the function, we create an instance of OpenAI embeddings. This class is used to generate embeddings of our document chunks using OpenAI's embedding model. We pass the OpenAI API key to the OpenAI embeddings constructor. This API key is required to access OpenAI's embedding model. We then create a FAISS vector store using the FAISS.fromDocs method. This method takes the list of document chunks and the OpenAI embeddings instance as input. The FAISS.fromDocuments method generates embeddings for each document chunks using the OpenAI embeddings instance and then creates a FAISS index from these embeddings. The FAISS index is a data structure that allows for efficient similarity search. We save the FAISS vector store to disk using the vector store.save local method. This method takes the directory where the vector store should be saved as input. Finally, we print the message indicating that the vector store has been saved to the specified directory. And here I'm just calling the create and save vector store function. Now let's define the load vector store function. This function is responsible for loading a FAISS vector store from disk. The function takes vector store directory as input, which specifies the directory where the vector store is stored. Inside the function, we create an instance of OpenAI embeddings, just like we did in the create and save vector store function. This is necessary because we need to use the same embedding model to load the vector store that we use to create it. We then load the FAISS vector store from disk using the FAISS.load local method. This method takes the directory where the vector store is stored, the OpenAI embeddings instance, and allow dangerous deserialization equal to true as input. Allow dangerous deserialization equals to true is important. It is sometimes necessary when using with FAISS. It tells FAISS to allow the deserialization of potentially unsafe data. Only use this if you trust the source of your data. Finally, we return the loaded FAISS vector store. Now let's define the ask RAG function. This function is responsible for answering questions using the RAG approach. This function takes question as input asked by the user. Inside the function, we first load the FAISS vector store using the load vector store function, passing in the vector directory variable. We then create a retriever from the vector store using the vector store.asRetriever method. A retriever is an object that is responsible for retrieving relevant documents from the vector store based on a query. We create an instance of chat OpenAI with temperature equals to 0 and the OpenAI API key. Temperature equals to 0 makes the model more deterministic, meaning it will give similar answers for the same question every time. Higher temperatures lead to more creative but potentially less accurate responses. We then create an instance of retrieval QA using the retrieval QA.from chain type method. This method takes the language model and retriever as input. The retrieval QA object is responsible for combining the retriever and the language model to answer questions. It first uses the retriever to find relevant documents from the vector store, and then it uses the language model to generate an answer based on the retrieved documents. Finally, we call the QA.run method to answer the question. This method takes the question as input and returns the answer generated by language model. The run method orchestrates the entire RAG process. It sends the question to the retriever, which finds the relevant documents. Those documents, along with the original question, are then fed to the language model, which generates the final answer. And finally, in this line, I'm calling ask RAG function with my question, and then I will get the response which we saw earlier in the video. So there you have it, a detailed walkthrough of the code. In the next video, we will try to convert this into a productionizable code base, and we will also create a Streamlit UI using which you can access this whole RAG system. So I'll see you in the next one. Happy learning.